All right, now that we're warmed up, let's look at an example. For any example, in any sort of model, you need to have three things. One is you need to write down what are the preferences of the agents in your economic environment. That is, what is it that they like and how do they value it? The next thing that you need to describe is the technology. That is, what are the means available to the agents in this economic environment to achieve their goals? And finally, you also need to include the information structure. It's not going to be too important in the example I'm going to look at now. So for example, let's suppose there is, just for simplicity, one person, and what they do is that they experience utility every period, and that utility depends on consumption, which is going to be C. However, this person lives at different dates. Let's index time by T. So we'll say that every date they are consuming C of T. In this case, we call this function U an instantaneous utility function because it tells you how they value consumption at any particular date. It doesn't tell us how it is that they value their entire stream of consumption over their lifetimes. So for that, we need to understand how the agent values consumption at different dates. And we're going to go with a simple and typical example, which is that there is a discount factor beta, and the agent simply cares about their discounted utility. If this were an environment with uncertainty, it would be discounted expected utility. All right. In this example, I'm assuming that the agent lives forever. If they don't live forever, then of course this is T. But the essence of dynamic programming is very often going to be that the problem that the agent faces may in fact go on forever. Now, how does this agent obtain consumption? Well, it turns out that this agent begins the period. Let's go back and say that they begin at date 0 with some amount of capital, which we're going to call K0. Now, what happens then is that with this K0, they actually have the ability to use it to produce other stuff. So the amount of output that they can make, call it Y sub T, at day T, is going to equal a function of whatever capital they have at that date, whether it's date 0 or not. And where does capital in the future come from? Well, what happens is that output has two uses. It could be used for consumption, or it could be used for investment. And what is investment in this context? Investment in this context is simply new capital. So the capital that you have available at a future date is equal precisely to the investment plus any capital that you have left over from today that hasn't worn out. So we assume that capital wears out at some rate delta, then what you have left over is going to be 1 minus delta times KT. Very good. Now, how might you solve this problem? Well, first, let's try and write it down as we would sequentially. If we assume that the utility function here satisfies local non-satiation, then we know that this is going to hold inequality. With equality, so we might as well impose that now. And now what the agent is going to do is, of course, maximize their discounted expected utility by choosing consumption and, I guess, investment at each date. subject to these, I guess, the joint constraint, we put all of these equations together, that consumption plus investment, actually we must be, if we impose the equality, equal to f of kt. Of course, we can actually simplify this because this is also a constraint. We could just combine them and end up more broadly with this. The consumption plus the capital that they have left over for tomorrow must equal this. We can simplify things further for this agent by taking their utility and, of course, substituting this in wherever we see consumption, because we can rearrange this easily so as to get simply that consumption is this at each date. By so doing, plugging that in here, we could end up with a different problem, which would be this one, but of course it's going to have the same solution. Now, let's say that the solution of this is something I'm going to call V, okay? Note that there is one thing that I guess is kind of obvious, which is that the agent starts the beginning of time, t0, with capital K0. We can think of this in two ways. One of them is that K0 is just another constraint here. But another is to consider that that means that if you change the value of K0, the solution to this problem is also going to change. That means that we can think of this V as being a function of K0. Great. That's the first thing. Now consider the following observation. Look at this problem. We can actually separate out this problem as follows. This is going to be utility at date 0, instantaneous utility at date 0, plus this problem going from date 1 until infinity. And that's very interesting, because if you look at this, this is exactly the same as the initial problem that we had here, except that it's moved one period forward. So now consider the following. Suppose I divide this whole thing by beta, so that this actually goes from t equals 0, but in order for that to be correct, I would have to write this. So now that's correct. And now again, look, this looks exactly the same as what we started with. There's going to be one difference though, of course, whereas when in this problem you start with V taking K0 as given, when you wake up tomorrow, you're going to start with taking K1 as given. So this suggests that maybe we can rewrite this whole thing as follows. Or more generally, we could say that what this agent is doing is every day is waking up, looking at the value of the capital that they have, and then taking into account how, through this constraint, they can best use that to get utility now, and while taking into account the fact that tomorrow they're going to be faced with the same problem. So then we can just think of this as being the same problem being solved at any date. And then we don't need to think about the infinite sequence. We just need to think about the agent's problem today. And then we would have everything indexed accordingly. Subject to this. So our first problem, the one up here, which thinks of, well, I guess you could call the sequential problem that this agent faces, you might solve using Lagrangian methods or Kuhn-Tucker-Karush theorem and so on. But this equation here is a whole different animal. I mean, this is positing that there is some sort of recursion to the agent's problem, and that has a lot of important consequences. If we can actually think of and solve this problem in this way, it also implies, for example, that the optimal policy, that is the optimal thing that the agent should do, by which I mean their optimal choice in this formulation of kt plus 1, is going to depend on one and one thing only. And what is that? It's kt. And if they were at some point in the future to end up for some reason with the same kt as they had today, then their optimal strategy would be to do the same thing. That's pretty powerful. The only question is, does this even make sense? Does it make sense to write down this problem this way? To put another way, is it true that there is a function that can be defined this way? How do we define something in terms of itself? And the fact is that under conditions that are pretty commonly satisfied by regular economic problems, the answer is yes. No, there is such a thing. There is a v that satisfies this equation. Second, if there is a v that satisfies this equation, one would ask, is there only one of them? Because what if there are two or three of them? Well, that would be a problem as well. So the next question is, do we have uniqueness? Is it true that there is only one unique solution to this problem v, which then we use to study the agent's behavior? And again, the answer is going to be that under circumstances that are regularly satisfied in common economic problems, the answer is yes. There will be one unique solution. Now I'm going to give you a quick outline of how this is going to work. The way we're going to try and show that such a thing exists is by showing that a way to think about this problem is the following. Suppose you take some function, I'm going to call it little v. And suppose this function v describes how this agent views the future. In other words, when they are trying to maximize this problem, what they have is a function small v that describes their understanding of how whatever capital they end up with at the end of the day is going to affect their future utility. Now, this, of course, is not necessarily going to describe the correct big V that satisfies this equation. So we're going to give this a different name. And of course, notice that now we have this not entirely arbitrary, but let's call it fairly arbitrary function V that describes how you view the future. Then what we have here would be another function that tells us what is the value of this agent deciding how to optimally consume and save if this little v describes their view of the future. So we're going to have to give this a different name. We're going to call it B of V. B here is what's called the Bellman operator. And what it is, since we're considering that it is a function of V, right? Change your V here that describes how you view the future. I'm going to get a different B of V. That means that this thing B is a function of V. It's a functional. It's a function that takes other functions as its arguments. Okay. Or alternatively, if you want to see it a different way, what if I'm going to call my function that describes how this agent views the future? Why don't we call it V0, where 0 doesn't indicate time. You'll see what it means in a second. Alternatively, we could just define this as V1. So we take V0, and now we have V1, which describes our view of the future. The 1 here actually corresponds to us having applied the Bellman operator once. Now, having done that, you could, of course, define, let's call it V2. What do I mean by that? Why don't we now take V1 as being the function that describes our view of the future, and let V2 be our current utility, given that we think V1 defined here is what describes how the future goes. And we could, of course, similarly define V3, which is taking V2 as our view of the future. And V3 is now how we maximize things. You could think of either of these in a different way. Again, this is taking V0, or little v, and applying to it once the Bellman operator. This is the same thing as taking V or V0 as our view of the future and applying the Bellman operator twice. Here we've applied the Bellman operator 3 times, and so on. And what we're going to find is that, well, in principle, you could do this as many times as you like, right? And what's really cool is that in the case of many economic problems that we're going to be interested in, what you find is that there exists a unique, let's call it V, such that limit as, let's say, n goes to infinity of Vn is V, the V we were looking for in the beginning, which of course is exactly what defines the V that we were looking for, right? It's a V, so that if you plug it in as the way you view the future, you recover that same function V. Moreover, you can also show that B of V equals V. Well, again, that's exactly what we wanted. We wanted a function that, if you plug it in as the thing that explains how you view the future, how you take the future into account when making your investment decisions, leads to the same function coming out when you apply the Bellman operator. And another way of looking at this condition here is, of course, that this is the limit of applying the Bellman operator infinitely many times to whatever function we started with. In other words, as long as we're starting with functions within the correct family of functions describing how we view the future, we will be able to converge to the correct value function. This shows that it exists, and this also shows us how to find it. Again, we can just start with any arbitrary view, again, within certain limits, of how the future is, and by just applying the Bellman operator repeatedly, which essentially means just computing this series, V1, V2, V3, as many times as you like, you can actually find it. This is stupendously useful because it also means that now we have a way of computing value functions. All we need to do, again, is repeatedly apply this procedure, compute this sequence here, until we have an error, let's say, between any two adjacent elements in this sequence that is sufficiently small that we can tolerate it. Very, very useful results. So in a later video, we'll discuss exactly what are the mathematics behind proving this result and how it is that we are going to be able to use this to study economic problems, such as the Killen and Prescott model that we looked at before. But in brief, what are we going to do with this? Well, we're going to take our function v, which is here, and we're going to plug this constraint into it. And we're going to get, of course, this function where we've now eliminated one of our control variables since it's not necessary. Now we take the first order conditions. Of course, what we're going to see is that if you derive the first argument here with respect to k t plus 1, you get minus u prime, and that is going to equal the derivative of v with respect to kt plus 1. That's the first order condition. But the second thing we want to do is, of course, we want to figure out what's this derivative. And let's do that. The derivative of v with respect to k, of course, k is not a choice variable here. So what we're really doing here is computing an envelope condition. It's as though kt is one of the parameters of this maximization problem, and we're seeing how the optimum changes when this parameter changes. That's one way to think about it. Of course, we're also going to get u prime here times the derivative of what's inside here with respect to k. Of course, that's going to be f prime of kt plus 1 minus delta, the rate at which capital breaks down, or the depreciation rate. Now we can put these two together, the first order condition and the envelope condition. So we're going to be very careful now to relabel everything to be at the correct date. We're going to end up with what's called a difference equation. It's a difference equation because it's telling us about how something changes over time in a discrete sense, as opposed to differential equation, which would be in continuous time. And this equation is called the Euler equation. The Euler equation is going to be the fundamental thing about this model that describes how it changes over time. Great. Now, in that discussion, however, there are a lot of things that I said as though they were to be easily understood and meaningful, but that actually carry a lot of assumptions in order for them to be meaningful. For example, I said that we should take the envelope condition by taking the derivative of v with respect to its argument k. Who is to say that v is differentiable? Nothing that we did so far has proven that. Also, going further back, we discussed existence, and we discussed that we could find v as the sort of limit of starting with some v0 and applying the Bellman operator repeatedly, and taking the limit as the number of times we apply the Bellman operator goes to infinity. What does convergence mean in this sense? What does it mean for the limit of something here, of a function rather, or a sequence of functions, to be something? In order for us to be able to say that, we would need to have a notion of convergence of functions. And we would want to do that properly rather than just speak of it loosely as though it meant something without having shown that it is meaningful. Also, this V0 that we started with, what is it? What kind of function could it be? What limits are there on what we can or cannot use as an initial value function there, or hypothetical value function there? Things like that. And that's why in another video, as I mentioned, we're going to be a bit more careful about these foundations that will take us into the world of real and functional analysis.